Okay, so welcome to the next recording. Um, so in the last class where we had finished off is essentially that uh, canonical system uh, will have an energy or will have a probability to have a particular value of energy very sharply peaked. So basically, a system will have a canonical system, a system which is in thermal contact with a reservoir, will have a particular value of energy. It will have fluctuations, but the probability distribution will be very sharply peaked at a particular value of energy with relatively small fluctuations about it. So we had derived an expression for the standard deviation or the variance in the energy fluctuations. Now the physics of that we will hadn't discussed. We just got the expression, but we'll discuss it. But we'll discuss it towards the end of today's recording. So we today start from a slightly different tack, from a slightly different point, but at the end we will come back to the fluctuations of energy. And in fact, that is how I will have taught also in the class. So the point that we will start from is something which you have already, well, you have seen the next slide. So what we'll first discuss is uh, show that when a particular system S, so this small system is system S in contact with a reservoir R, and this system has suppose energy Es and the reservoir has energy Er. And if there is an if the reservoir say takes a certain amount of energy dq from from the system, or if it gives it away some energy dq from the system. And remember that we have discussed that on exchange of relatively small amounts of energy dq, small as compared with the energy of the reservoir with much larger degree of freedom and much larger energy than the energy of the system, and thereby the amount of energy exchange between the system and the reservoir dq will also be significantly small compared to the energy of the reservoir. So if the reservoir takes some energy dq, the amount of entropy change for the reservoir will be dq by t, and that is a concept which you know from thermodynamics, but we'll approach the same problem from statistical mechanics. Now, suppose if the reservoir had energy ER, the number of microstates available to the reservoir would be omega ER. R stands for reservoir, right? And however, if the reservoir absorbs, just assume that it absorbs some energy from the system dq, then the energy of the reservoir will be Er plus d bar q, which is a larger amount of energy compared to Er, and thereby it will be accessing a larger number of microstates as well. Now you're taking the log of omega, the number of microstates, with energy Er plus dq. And remember this is statistical mechanics because we are using the expression for Boltzmann entropy on absorbing an amount of heat dq. So what we are going to calculate is change in Boltzmann entropy. We have associated kb ln of omega with statistical mechanics and entropy. And when we are using this expression to denote the entropy, we are calling it Boltzmann entropy as different from thermodynamics entropy. So what we're going to calculate is basically the change in the number of microstates, or rather change log of omega ER plus DQ, the number of microstates available to the reservoir when it has a slight more energy, DQ, and minus when the reservoir had energy ER. And I'm taking log of that and multiplying it by KB to keep it, to associate this quantity with DS, the change in entropy, change in Boltzmann entropy. And this can, of course, I mean, this can be written in terms of a Taylor expansion, where we are calculating this equal to log omega ER if it is on the right hand side of the equation, and when you bring it to the left hand side of the equation, it becomes with a minus sign, and then del del ER log of omega at ER. So this differentiation, after doing the differentiation, we calculate it at when the reservoir has energy ER. So we are writing that's why ER here into DQ, because rate of change of log of omega with energy ER, and then the amount of energy which has come in is DQ, plus half double derivative with respect to energy ln omega DQ whole square, and so on and so forth, plus higher order terms, right? And this can be associated, because it is close to the supposed equilibrium energy ER, then this can be associated with the temperature of the reservoir, which does not change. We had shown in the last class that if the reservoir absorbs some energy dQ, then the temperature remains relatively unchanged on absorption of dQ. So it remains TR, the temperature of the reservoir. And moreover, we had also shown that the rate of change of temperature, beta is 1 by temperature, but if temperature doesn't change, 1 by temperature is also not going to change. The rate of change of temperature with ER is relatively zero if we are talking about a reservoir, if we are talking about a reservoir with large degrees of freedom and large amount of energy. So the second term becomes equal to 0. This we associate with the temperature of the reservoir. So what we have on the left hand side of the equation is ds, Boltzmann entropy, and on the right hand side, if this beta, remember we had multiplied the entire equation by kb, and beta has 1 by kbt, so kb cancels, and what you have is dq by t. And remember, a change in entropy due to absorption, there's no change in volume, right? There's no work done. So that is the change in entropy of the system, dq by t, but that is also thermodynamic change in thermodynamic entropy, right? Change in amount of heat absorbed, say, by the temperature, which for the reservoir is the amount of heat absorbed doesn't change the temperature of the reservoir. So this T corresponds to the temperature of the reservoir. So dq by T is the thermodynamic entropy. So the Boltzmann entropy, or change in entropy of the system calculated using statistical mechanics in terms of kb log omega, the Boltzmann entropy, is very much consistent with the phenomena of heat entropy change, thermodynamic entropy change. It's the same dq by t. This is a further consistency check that kb log omega does indeed behave like the quantity entropy that we know from thermodynamics. So that's the first point to make. Then the second point to make is, as we have discussed in the past, that suppose this was a reservoir with capital F with much larger degrees of freedom than the number of degrees of freedom of the system S, which has energy S, then we had shown that the probability that the system will be in a microstate with energy ES depends, or the probability depends upon the number of microstates that the reservoir is able to access after giving energy Es to the system. So if the reservoir had all the energy, it had all the energy possible, Er plus Es equal to E0, it would have a large number of microstates, but it prefers to give some energy Es to the system, and thereby it has a lower amount of energy, Er, and the probability that the system can have the energy or can be in a microstate with energy Es depends upon the number of microstates that the reservoir can access. So this is a pretty subtle point, but please remember that. And so what we had said, what we had shown, so we had argued that the probability will be, but we're going to make it more formal today. So what we had shown is that the number of microstates that the reservoir will have when it has a energy Er. Energy Er is E0 minus Es. So that's what I've written, R for the reservoir, and of course taken a log. So we're going to do a Taylor expansion, not in terms of omega, but in terms of log of omega. So the number, so this log of omega E minus E0 will be equal to log of omega E0. So when this reservoir has the entire amount of energy E0, right? Plus correction terms, Taylor expansion correction terms, del del E of ln omega calculated at E0, right? So that's what defines the temperature. So del del E ln omega calculated at E0, it has the entire amount of energy into minus Es, because it has given away some energy to the system. And from this you get ln omega R E minus E0. When this term comes to the left hand side of the equation, it becomes minus, and thereby it goes to the denominator. So log R is 0. So there's a ratio, you get this ratio, and that is proportional to minus Es, and this quantity is associated with beta, which is 1 by kBt. Beta equal to 1 by kBt, and that is what it is equal to. Now, and this is taken from Rife section 6.27 6.2.7. What one could write is thereby that the number of microstates that the reservoir has access to when it has given energy Es to the system decreases exponentially as e to the minus Es by kBt product into the total number of microstates that was available to the reservoir when it had the entire amount of energy E0. Yeah. So this, the number of microstates decreases exponentially compared to omega R is 0. Now, if we divide it by the total number of microstates possible for the reservoir, okay, on both sides of the equation. So suppose the reservoir has energy E0, it has energy ER dash, it has ER double dash, it has also ER E0 minus ES, right? You basically sum up by the total number of microstates available or accessible to the reservoir. Then you know that now we are looking at the entire system. Now, if you just focus on the reservoir, this number of microstates, the ratio of this and this is essentially the probability that the system will be that the reservoir will be uh, will give away I mean, this is the probability that the reservoir will have system ES energy, right? The number of microstates available to it, and correspondingly, the system will have energy ES, and it will explore all possible kinds of microstates, right? So that the system will be in a particular microstate with energy ES is decided by omega r E0 minus ES, right? And the probability, and that decreases with exponential E minus capital ES by kBt, right? This is decided by this quantity, and this in turn decreases as this with the normalization constant. So ES can take different values, and correspondingly, the reservoir is going to have different values of ER, right? And the sum over I, all the microstates. Now the focus is going from the reservoir to the to the system, which is exchanging energy with the reservoir. So the probability that the system will be in a microstate with energy ES was proportional to e to the power minus ES by kBt. And if you sum over all microstates that the system can take, then that should be equal to 1. Right? The probability was proportional to e to the power minus ES by kBt. This was some factor, and the aim is to figure out an expression for this normalization constant. So if the probability is proportional to e to the power minus ES by kBt, let's say it is proportional to C into e to the power minus ES by kBt. Now we also know that the sum of probabilities has to be equal to 1. Hence, we could say that this normalization constant, whose value we didn't know, and we wrote that the probability has to be proportional to e to the power minus ESI by kBt. We are summing over all microstates. Different microstates could have the same energy ES. Some of those microstates are going to have the same energy ES, but some of those microstates are going to have different values of the energy. I'm recording. I'll call you back in some time. So it can have different values of microstate, energy. So, and you're basically summing over all the probabilities of all the microstates that the system can have. So I'm writing the word system. Here the focus was on the number of microstates that the reservoir could have. That decided the probability of a particular microstate of the system with energy ES. Now the entire focus is on the system, and we are summing over all the probabilities of the different microstates of the system, and that is equal to 1, and that is equal to a constant, right? A constant whose value we need to figure out. And since each microstate was had a probability C into e to the minus ESI by kBt, or beta ESI. This summation is over all microstates. This equality holds, and hence C is equal to 1 upon summation over I runs from all microstates that the system can access with different values of energy. This stands for system. I stands for the different microstates that the system can access with various values of energy into beta, and that is a 1 by this sum is what this constant value is. Now whatever is in the denominator, that is denoted by Z. So Z is also called the partition function, and we'll see later that it is related to the free energy of the system, and then the probability that the system is in a particular microstate I is e to the power minus beta EI. EI is the energy of the microstate by the normalization. So C was Z, where Z is this quantity. Okay, so this is what I want you to uh, I want you to keep in mind. And of course, the aim is to figure out a physical interpretation for Z. So Z itself doesn't have any meaning, but minus kBT ln of Z, as we'll show in 2 slides, has the meaning of the free energy of the system. Okay, to do that, we do a slightly different calculation. What we do first is to calculate the average energy of system S, and this is taken from section 6.5 of RIFE. And so note, what I'm calculating is the average energy of system S, which is in thermal contact with the reservoir. So system S can take different values of energy. For different values of energy, it can also access different microstates. And to calculate the average, what we need to do is calculate the canonical ensemble average. Remember canonical ensemble? So when the system has a fixed number of fixed value of energy, the particles, if it is made up of particles, gas particles, then they can exchange position among themselves, and all of them will correspond to a different microstate. For a particular fixed configuration, the system can also take different values of different value of momenta, as long as its energy is Es, say a particular value, and those again correspond to different microstates. But now the energy itself of the system can change. So if you like, it is a sum over a much larger set of microstates than what it would have if its energy was fixed. So for a particular value of energy, it has a certain set of microstates. For different values of energy, when it takes more energy from the reservoir, it will have a different number of microstates. So here, the canonical ensemble is a much larger set of microstates for the system compared to if the system had a fixed amount of energy. And when we are and of course, different values of when the system has different values of energy, the probability of accessing those microstates are different. It is depends upon the energy of the microstate by this normalization constant. So lower values will have lower uh, will have the probability of accessing that microstate will be lower, right, compared to higher values of energy. So this note, this average value of energy is essentially an ensemble average. There's no time. This ensemble is as the system goes from evolves in time. In reality and experimentally, what you would have is an experimental system is going to go from one microstate to the other as a function of time. But when you are calculating this average, you don't have time in the picture. What you have is the system itself is like exploring different microstates. All of those microstates are all at once mentally available to you, and you are basically just calculating what is the energy of a system when it was in a particular microstate into probability of accessing that microstates, and sum over all possible microstates gives you the average value of the energy of the system. Note that there is no time here because this is an ensemble average. You are not saying that the system is gradually going from one to the other. You are saying that you have all copies of the system as the system would evolve over time, over infinite amount of time, as it goes from one different microstate to the other. Not infinite, it has to be ergodic. So all microstates have to be accessible in a finite amount of time. So what you're saying that you have this entire set of microstates all at once. Energy of the system when it is in a particular microstate I, probability accessing over accessing that microstate, sum over all I. And then this Pi can be written as e to the power minus beta Ei upon Z. Note, this is the same thing as Z, sum over I, e to the power minus beta Ei, all microstates. And here it comes with an, so this energy I is I. Sum over all microstates. I've repeated that many times. Please note that. Now this Ei, so now I'm doing some mathematics. This is just some algebra. This Ei can be written as, so del beta of e to the power minus beta Ei, right? And so if you take a derivative basically with respect to beta, then the Ei would come, minus Ei would come. So you would, so this expression is equal to, so this is intact, Z. I've taken the del beta out of the summation, and then it's e to the minus beta Ei. So if you make this operate on the sum, you will get this Ei. So for each value of energy, it would simply sit here. And this in turn can be written as 1 by Z, right? This is nothing but the partition function, and it's del Z del beta. And this in turn can be written as, this was a mathematical operation, minus del beta ln of Z, right? So what we have got is that the average energy at constant volume and n, because the system has fixed volume and n, that's not changing. We're talking in a canonical ensemble. The average energy of the system, statistically average, note this is a statistical expression that we used. This was basically canonical ensemble derived from deriving canonical ensemble from the microcanonical ensemble. So this is statistical physics. The average energy of the system is related to minus del beta ln of Z. But if you have a system and you're looking at it thermodynamically, so what do you associate the average energy of the system with? It's the internal energy. So it's here that we are associating the microscopic quantity, average energy of the system, with the mean energy of the system, the internal energy, the thermodynamic internal. So here is the mapping that we do. Okay, we are associating it. Next, if you've gone through lecture 5, we had there defined a quantity called the free energy, which was U minus Ts. And just to remind you that dF, the change in free energy, was the maximum amount of work that could be obtained in an isothermal process, right? So if you have to do some work, then of course there has to be some change in the boundary conditions, let's say volume, and dF was the maximum amount of work done when the temperature of the system was held fixed. It was in contact with a heat reservoir, right? So temperature is not changing in an isothermal process. That was the maximum amount of work, the physical meaning of the change in the free energy, F. And if you don't remember it, please go back and revise lecture 5. Moreover, if a system was if there was a process which was isothermal and isochoric, which means even volume was not changing, it means no work done, right? And if under such conditions, and if the system was not in equilibrium, it was isothermal, all the processes allowed, the temperature must remain constant and volume mustn't change. In such conditions, the system would reach equilibrium when its free energy was minimized. If once it's reached its minimum free energy, it would remain there because it can't go to minimum. But if we change the conditions without changing the volume and the temperature, then there's some gradient in concentration or something like that, some process, so that volume, there's some process, number of particles has to remain constant, but suppose there's a density gradient, then the system would evolve in such a manner that the new system, the newly evolved system F2, had a lower free energy than the previous system. But once it had reached its minimum free energy, it would remain there. Right? So free energy is a state function which would minimize itself to reach equilibrium in a in conditions where the temperature doesn't change and the volume doesn't change. Volume is fixed, number of particles is fixed, and so thermal temperature is fixed. So for that, to describe the condition for equilibrium for such a system, the free energy was derived or was established, or it was defined, and that was done in lecture 5. So here we are going to just use some of the properties. This was just a quick revision, I mean quick giving an intuition of the physics of free energy. And doing some algebra, df could be written as minus p dv minus s dt, right? So when you are changing volume, temperature is remaining fixed, and when if you're changing slightly the temperature, volume is kept fixed, and then del F del V, rate of free energy with volume constant n and t, is related to minus p, and the rate the rate of change of free energy with temperature at constant volume and n is related to minus s. This is just let's look at the, f is a function of essentially t and v and n and so on. Now we are writing this f slightly differently. We are writing the internal energy of the system. Note this was all thermodynamics. This is class 5 was thermodynamics. We are writing the internal energy of the system as F plus Ts, where S, using this formula, we are writing it as minus del F del T at constant V and N. And after that, we are just doing some algebraic manipulations. We can write this F minus T del F del T as minus T squared del del T of F by T at constant V by N. And why can we write that? If you basically take the derivative of with respect to t of f by t, you get minus f by t square plus 1 by t del f del t. And if you multiply by minus t square, you'll see that you just get back this. So basically, this is equal to this. We're just writing this in a different algebraic form or mathematical form. And this in turn, because of 1 by t square here, can be written as del del t of f by t, derivative with respect to 1 by t. Just work it out, you'll get it, right? So that's what it is. So this is equal to this, and this in turn is equal to derivative with respect to 1 by t. And if you multiply on both sides by kb, right, or rather 1 by kb if you like, 1 by kb if you like, you will get so 1 by kb and 1 by kb, I mean really doesn't matter, numerator and denominator, you get f by kbt by del del t of 1 by kbt. Kb is some constant, later figure out to be Boltzmann constant. And this, so here till now it was all thermodynamics. Here also it's thermodynamics. Kb is some constant, and we are getting del del beta is f by kbt. We are just redefining the variable here. But note, this energy of the system is now being written as f 1 upon kbt del del beta. And in the previous page, we had got this average energy which we had associated with internal energy and written this. So this u we can write as minus del del beta of ln of z. So this was a thermodynamic relation. This is a statistical mechanics relation. We are saying that since both relate to the internal energy, which is equal statistical physics wise to the average energy of the system, we are writing it, we are introducing it. You say, okay, let us do this and see what happens. And what we get is, if this happens to be true, and even in the past, we were associating quantities calculated statistically with thermodynamically calculated, with quantities which were understood thermodynamically, and we saw that things were pretty consistent. It had all the right properties. Here, what we are doing is associating again the internal energy with the average energy of the system. This is the expression for the internal energy. This is the expression for the average energy of the system, and saying if they has to be equal, if we want to get thermodynamics out of statistical mechanics, then F, the free energy, has to be equal to minus kBT log Z. It was an association that we did, and we say now that if we calculate Z, and if this association holds, because both are describing the energy of the system, let's see how far we go ahead. So we'll establish that, but slowly, one by one, right? So we associate minus kBT ln of Z with the free energy of the system, because the derivative of this quantity gave the internal energy of the system. Okay, before going further, let's and we'll of course discuss free energy more, but let's discuss a bit about energy fluctuations again. So the system had a certain value of energy, E bar. And the question is, how much does the system, the energy of the system, deviate from E bar? Okay, so let's calculate that. So what we have already shown in the previous slide is the internal energy, which we associate with the average energy of the system calculated at constant volume and number of particles, can be written as EI, PI, and that was in turn e to the power minus beta EI by Z, I summation over I is over all microstates, and that was written in this form, right? We are just writing it in this form. Now what we are calculating is del U del beta, change of energy, internal energy or average energy with the temperature. If you like, beta is 1 by inverse temperature. So we're calculating this, and we're going to show that it is related to the fluctuations of energy of the system, or fluctuations of energy of the system with a minus sign. So del U del beta equal to minus fluctuations of energy of the system. Actually, it is equal to the square of the fluctuations of the system. If the fluctuation of energy of the system is characterized by the standard deviation of energy, of the energy distribution, then the square of that is the variance, and the variance is so we'll just see that the expression for variance of a system is E square. So it's E square bar minus E average square bar. But we'll see after doing some mathematics, it comes with a minus sign. So if you took the minus sign out, it would be within brackets E square bar average, ensemble average, minus E average whole square. And the way we get this is del U del beta can be written as a derivative of the numerator, keeping the denominator intact. So the denominator is 1 by Z, and this is the derivative with respect to beta of the numerator. And here we keep the numerator intact and take a derivative with respect to beta of the denominator. So if you take the derivative of with respect to the denominator, we get minus 1 by Z square, but we have to take, we have to take the appropriate derivative of this as well. So that when we take a derivative with respect to beta, we get this minus EI coming in, right? So this is these two terms. The product is the derivative of the denominator, where this term remains intact here. And this in turn can be, when you take a derivative with respect to beta, you will have ei squared with a minus sign, because every time you take a derivative, it will come out with a minus ei. So you have minus ei e to the minus beta ei by z. But this thing is nothing but e square average ensemble average, because whatever quantity you want to take, x, xi, pi, sum is the mean average of that quantity. Here that average quantity is ei square. So you are basically getting e square average ensemble averaged. So this is ensemble. So pi is e to the minus beta ei by z into minus ei square. So you're getting that quantity here. And from here you had this summation 1 by z square into this. So you have this summation into this summation. Instead, if you write a z here and a z here, that is essentially, if you think about it, it's the ensemble average, mean average energy of the system. So you get E average whole square, right? And if you take the brackets out, E square average minus E average square is the variance. It's a measure of the fluctuation of energy of the system, and that is exactly what you get with a minus sign. Just to summarize, what you get is del u del beta equal to minus E square average minus E average square, and that is equal to the variance in the fluctuation of energy. Right? It's a sigma is the standard deviation, and sigma square is the variance. That's a measure of the fluctuation. So standard deviation is a measure of the fluctuations in energy, and square of that is the variance. That is equal to with a minus sign del u del beta. So that was statistical mechanics, because we started from this expression and then took the derivative of this quantity. If you like, we took the derivative of del u beta, or we took the derivative actually of this average value of energy which we associate with the internal energy, right? So we could have as well written, we actually are using this expression for this. So we are using it. So here, though I'm written u, we are actually using expression for E bar to do this entire calculation. E bar is the, like expectation value of E, which is the average energy of the system, which we associated with U. And here we are actually calculating the thermodynamics internal energy, del U del beta, which is del U del T into del T del beta at constant V and N. And we keep this term intact, and del T del beta can be written as, since this is a partial derivative, it can be written as 1 by del beta del T, and that's exactly what I have written. And this in turn, if you calculate this, this is minus 1 by kBt square. When you put it in the numerator, it becomes minus kBt square into del U del T at constant V. Now, what is change of energy, internal energy with temperature at constant V and N? It is Cv. So what we have, if you write like, is del U del beta, which we said is related to the fluctuation in energy with a minus sign. And here also you have a minus sign. So what you have is this variance of energy, the sigma square, if you like, is equal to minus kBt square Cv, which we write in turn as, so this was Cv of the system, del U internal energy was energy of the system. Now this we write in terms of n, if suppose there are n particles. So the Cv of n each particle into the total number of particles. So we are basically writing it the Cv per particle, or Cv per degree of freedom of the system, if you like, right? If n was the degree of freedom, if there are n particles, then I'm writing it as Cv. Which in turn, in that case, we get that the fluctuation, which is the standard deviation, goes as T into root n. So more the number of degrees of freedom, more the fluctuation, right? But what we really need to look at is the relative fluctuation or delta E by E. So let me give you an example why delta E by E is relevant. So what it says is that the fluctuation, the standard deviation, goes on increasing as t by root n. Okay, of course, assuming that CV remains unchanged, CVN remains unchanged. In practice, it could be a temperature dependent quantity. So in that case, the temperature dependence of CV would have also come into this expression, but at the moment, let's assume that it is constant. And let's look at the meaning of this algebra where we are writing delta E by E. So I'll just talk of a different example, then come back to it. Now, suppose the volume of my body. Okay, let's assume it is 70 liters. Okay, 70 kgs, 70 liters. I might be 80 kgs actually, but doesn't really matter. What I could say also, by the way, my since I'm breathing in and breathing out, my volume is changing by 0.5 liters. Suppose one breath of mine is 0.5 liters. I breathe in, and this is my volume has increased by 0.5 liters. An elephant, when it breathes in, suppose it breathes in by 5 liters of air, and its volume increases by suppose volume increases by 5 liters, right? So bigger the system, bigger is the volume change. But is that a huge amount? What you need to know is my volume, let's assume my volume is 100 liters for simplicity, and suppose I breathe in and my volume changes from one set of 5 seconds to the next set. The percentage volume change is actually 0.5 liters by 100 liters. That's 0.5%, right? So that's not much. So it sounds, oh, my volume is changing by 5 liters. Hey, sorry, half a liter. But with respect to the total volume of my body, right, half liter is not too much. It's basically my volume average remains constant, though my volume is changing by half a liter. Elephants, suppose is weight is, I don't know what the weight of an elephant is, but suppose it is 500 kgs, and it is taking in a breath, so that its volume increases by 5 liters. Yeah, so that's a lot. That's much more than me. But with respect to its body, this change in volume is minuscule. It's 5 liters by 500 liters if its volume is 500 liters. And that is just 1%. Right? So similarly, the fluctuations in energy is going to increase with the number of degrees of freedom. What you really need, okay, it might be a huge change, but if the energy itself is huge, then with respect to that, that fluctuation might be minimal. So that's why what we are doing is delta E by E, and then it comes out to be T root n, and what is average energy of the system? It's U0 n. Suppose the average energy, you break it up again into the energy per degrees of freedom. So U0 n by n, and that goes as 1 by root n. Now, of course, CV could be a function of temperature, and similarly, the internal energy of the system could be a function of temperature. So we should not, and especially if you are near the critical point, CV can increase. You could have a singularity. You could have a singularity in the CV. So we are not going to discuss this. We are not going to focus much on the temperature dependence. Of course, yes, with increasing temperature, the fluctuations can increase, but the nature of fluctuations increase with respect to temperature is a more complicated topic, which we will not touch at the moment. If there's a singularity, these fluctuations can increase in a huge manner. So we'll just focus that the fluctuations in energy with respect to the mean energy of the system, the relative fluctuations goes as 1 by root n. And if n is very huge, then this relative fluctuation actually decreases. So this thing, as actually if n is big, then this relative fluctuation is extremely small, and it increases with the number of degrees of freedom of the system. Uh, so this is a discussion on the fluctuations in energy, which we had also discussed in the where we had ended the last class actually. And what we had written there is after some discussions, we had basically shown that the fluctuations in energy, again, though we had approached from a different perspective, was equal to Es max into kBt. Now, this thing can behave in a relatively complicated manner with temperature, but if we again write it, the fluctuations in energy as Es max by the number of particles in the system, we have multiplied by ns and divided by ns, then this is energy per degree of freedom, if you like, okay, into kBt. Now this we write it as C1, some energy per degree of freedom, and delta E. So the square, I have taken the square root on both sides. So delta E, or this is essentially sigma, the standard deviation, goes as root ns into C1 kBt. Now this C1 of course can depend in a complicated manner as a function of temperature, but we are not focusing on that. Suppose at the same temperature we divide this by the Es max. So this we were calculating, we were taking fluctuations of energy about the peak of the probability distribution, and the energy at the peak of the probability distribution was Es max, and that if it is very sharply peaked, Es max has to be very close to the value of the average energy of the system, or the ensemble averaged mean energy of the system, right? And that's what we were working on just before I entered this. And this Es max in turn can be written as the number of degrees of freedom, the number of particles into energy per particle, right? That is energy per particle. So we have again used this, and then again we get so this. I think we should be getting a square root kBt also, because here there was kBt and there's kBt. But we will not focus on the temperature dependence. We will rather focus again delta E by Es max. We are getting as this relative fluctuation was decreasing with the increase of number of particles of the system. It goes as 1 by root n, and that is the focal point of this class. Now, the other point that I want to discuss before I end today's class is uh, wait, so there was something else. Yeah, so in the previous class we had also discussed that uh, that the probability that the system will be in energy for a particular value of energy is related to the product of the number of microstates with that energy into e to the minus es by kBt, and it was a very sharply peaked distribution. And how sharply peaked? A measure of the standard deviation. So delta E is the standard deviation, sigma if you like, and delta E whole square is essentially the variance, right? And both in today's class And in the end of yesterday's class, we showed that the relative fluctuation or the relative fluctuation in energy with respect to the mean energy goes as 1 by root n. So that's, and if n is large, this quantity is extremely small. Okay, delta E will be larger as n increases, but with respect to the mean energy, it will be very sharply peaked, and that is the message. So we had also discussed, so this is section 3.7, that the probability that the system will be in energy Es will be the C, and the C we calculated today as the partition function, right, into number of microstates with the energy Es into e to the power minus Es by kBt. So it is not just exponential. With energy Es, it will also have this factor. So we also discussed in today's class that Z was equal to sum over all microstates. Some of the microstates could have the same value of energy Es, and the probability of accessing a particular microstate is e to the minus beta Ei by Z. And this in turn can be written as the number of microstates with energy Ep into e to the power minus beta, there should be a beta here, into Ep, where the sum is the different energy values of S. So this was sum over microstates. Here it was a sum over different energy values of S, and this was confusing to some students in the class. So what I've done is written Z sum over all microstates, right? This is what I've kept on saying. I is sum over all microstates. This I've written explicitly as e to the power minus beta E1 with suppose some set of coordinates of the position and some set of coordinate values for the momenta. Now, the system S can have the same energy E1, but with the positions a bit. So suppose the gas particles have moved, the energy remains the same E1, the energy of the the energy of the system remains same E1. So the probability, sorry, not the probability, but when you're doing the sum, you could have, it could be in a different microstate with a different set of positions and also a different set of distribution of momenta. Here I've also written P1, P2. So X1, X2 has gone to X1 dash, X2 dash, and similarly P1 to P1 and P2 and P3 and up till Pn will go to P1 dash, P2 dash, P3 dash, Pn dash. So there's a different distribution of momenta, and you could have a different distribution of position as well. X1 dash, X2 dash is different from X1, X2, but it could have the same energy, E1, right? So this sum is over all microstates. And then you could have again e to the minus beta E1, a third microstate where you have X1 double dash, X2 double dash, P1 double dash, P2 double dash, and so on and so forth. So since the sum is over all such microstates, this all microstates which have energy E1, and there can be so many microstates by changing X1 to X1 double dash, X2 double dash, X1 triple dash, X2 triple dash, similarly for momenta. So note, the sum is over all microstates with the same energy, and the number of microstates with the same energy E1, suppose similarly, I mean, if you go on, the number of microstates might be omega 1 E1. But the sum is over all microstates, and the system could be in a different energy as well. Hence, this plus continues, plus e to the power minus beta E2, X1, X2, and if E2 is more than E1, then the number of microstates, the number of the number of ways that the system can distribute its energy will be more. So P1, 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 P2, P3, P4 with its different sets of, so such that the total energy remains E2. Moreover, suppose there is another microstate with the same energy E2, but x1 dash, x2 dash, x3 dash, similarly p1 dash, p2 dash, p3 dash, plus e to the power minus beta E2. Its energy remains the same, but the microscopic decrease, the value of the microscopic x1 has become x1 double dash, x2 has become x2 double dash, similarly for p1, p2, and you can have that in various kinds of way. And the number of microstates that you can have with the same energy, let's suppose that to be omega 2 E2. So this should not be P, but E2. And similarly, the system can take a different value of energy E3, and you can have different microstates, x1 dash, x2 dash, x1 double dash, x2 double dash, similarly from moment plus various microscopic coordinates which have the same energy E3. And similarly, it could have energy E4 and E5 and so on and so forth. And remember, when the energy is E1, the total number of microstates of this summation was the number of terms here with energy E1 was omega 1 E1. When it has energy E2, the number of microstates was the number of terms in the summation was omega 2 E2. When it had energy E3, the number of terms that were there were omega 3 E3. And Z is a summation of all of these, all this, plus this, plus this, plus so on. And this in turn can be written, so this is sum over all microstates, and we are saying sum over all energy of the microstate. It should not be energy levels, but this is wrong, this levels is wrong, this is the energy of the microstate P. The system has to be an energy, right? And you can also write this as omega P. The energy is EP, like E1, E2, E3, EP. Correspondingly, it will have different number of microstates with energy EPs, hence omega P. And the probability, and not the probability, it has to be just multiplied. I mean, if you had, yeah, so probability is e to the minus beta, yeah, but minus beta EP, where the sum is what the energy of the microstates, right? This is sum over all microstates, this energy of the microstates, not level. I'm repeating again. Just to give you an example, I intend to give you an example. We'll take a very simple case where we'll not worry about quantum mechanics and so on and so forth. So just suppose that there are 4 energy levels, E0, E1, E2, and E3. And there were 2 particles, and suppose they were fermions, or the only property of fermions that we are using, or they had behavior like fermions. If they're identical and there were no spin degrees of freedom, just as an example, suppose that in one energy level there can be only one particle at a time. That's the meaning of the word. That's the sense that I'm using. So any particular energy level, not more than one particle can occupy. Then, and if this is your system and it is in contact with a heat reservoir of temperature T, then one of the microstates would be when one particle is in energy here E0 and the other particle is in energy E3. So this would be microstate number 1, because there are only 2 particles. So all the possible ways it can arrange itself, right? And a second microstate will be when this particle is here, one of the particles is here and the other particle is here. A third microstate will be when one of the particles is here and the other particle is here, right? Another microstate would be, so only the microscopic degrees of freedom is changing, but note the total energy of the first microstate will be E0 plus E4, E0 plus E4. The energy of the second microstate will be E0 plus E1. The energy of the third microstate would be E0 plus E2. And you could have other microstates in the sense that E1 plus E4. Yeah, one particle is here and another particle is here. Another would be here, and the last would be here. And it would all correspond to different energy of the microstate. And remember, this system is taking different values of energy. It means it has to take energy from the heat bath or give away energy to the heat bath. So the partition function would be e to the power minus beta energy of the microstate. Note, not the energy level, though I wrote here, it is energy values taken by the microstate. So this is energy values taken by the microstate. This is energy values taken by a different microstate, different microstate, different microstate. So Z is e to the power minus beta energy of the system when it is in a particular microstate, energy of the system when it is in a different microstate, energy of the system when it is in a different microstate, and so on. Here only 6 microstates are possible. So this is Z. And the probability that the system is in the first microstate with energy, say, E0 plus E4 is e to the power minus beta E0 plus E4 by Z. That's the first microstate. Here, there's no degeneracy, means when if the system had energy E0 plus E4, the number of ways it can do that is only one. So if you like this omega p EP for a particular value of energy EP equal to E0 plus E4, omega 1 equal to 1. Omega 2 for the second microstate again is equal to 1 in this example. But in other cases, you can have a large number of different microstates. And finally, I would like you to, before ending the lecture, I would like you to contrast it with the microcanonical system. Now, suppose there was a different case, a different system, again fermionic in the sense that in one or even it was bosonic. I mean, suppose the total the energy levels were E0, 1 E0, 2 E0, 3 E0. So this is basically different integer values of the same value E0. Here we had taken E1, E2, E3. We had not given any relation between E0 and E1, E1 and E2. We had just kept it arbitrary. But here we are really giving it, this is 1 times E0, and this is 2 times E0, and this is 3 times E0, and so on and so forth. And suppose the total energy of the system S, and suppose the system was isolated. It couldn't take energy from some thermal reservoir, which corresponds to a microcanonical ensemble. It's an isolated system. Okay, all microstates are equally probable. Here, all microstates are not equally probable. But if it's an isolated system, and suppose the total energy which was allowed was S equal to 5E0, then only 2 microstates would have been possible. That one of the particles is here and the other particle is here, so that the total energy is 5E0. The only other microstate which would be allowed, I think there's something wrong. I have put this is also 1 E0 and this is also E0. Okay, so just ignore this level if you like. Just ignore this. This is wrong. This need not be here. This and this are identical. Right? Oh, okay. Okay. Suppose this was some other energy level, the same value is 0. It had some other quantum number or something like that. Then the number of microstates which would have been allowed is this and this, this and this, and this and this. Then 3 microstates would be allowed. But suppose there was no degeneracy, this and this were identical, then only 2 microstates would be allowed. I think it's better that you consider this and this identical, because in a recording else it might get too confusing. So I'll finish my lecture here. We'll continue next time.